Hi everyone. Today we're going to be talking about electronic configurations and orbitals. So in your textbook you will have hopefully read the sections 2.5, 2.6 and you may be a bit confused about some of these terms and the way that it explains things. Basically we have a few different types of orbitals. We have s orbitals. These are just a spherical orbital, so if we look at an x, y, z plane, an s orbital would just be a sphere like this. And then we have a p orbital, and again if we have our x, y, z plane, the p orbitals are really like these balloony looking shapes. That would be one p orbital. You would denote this the p subscript z, and you'd also have this py orbital. Py, and we'd also have a px orbital. These p orbitals aren't actually fixed in x, y, z directions. It's just that's the notation that we use for them. They are, distributed orthogonally through space. So we have these p orbitals, and then we have the d orbitals, and they're similar in shape to the p orbitals, although a little bit more confusing. I guess more detailed. There's more of them. There's 5 d orbitals, and your book doesn't have a picture on those orbitals, and it's hard for me to sketch a lot on top of each other, but they'll often go out in a plane itself. So you'd have a p xy orbital, which would be in the xy plane. Sorry, a d xy orbital, which would be in the xy plane, and so forth. We won't worry about that, but just know that it looks something similar to a p orbital. And how does this all relate? Well, with your periodic table, we have our this is known as our S block, and so really helium would be over here too. And so you'd have 1s, 1s1, 1s2 for the helium. The one at the start indicates the rho. It's really talking about the principal energy level, which you're not expected to understand, but just know that the rho that you're in, the period, indicates the energy level of these particular orbitals. And so we have our 1s, 1s1, 1s2. I'll show these in more detail in a minute. And then you'd have your second row, and you'd have your 2s1, 2s2, and then your 2p's. Okay, so let's have a look at the section in the book that is relevant for that. And so hopefully you can see on page 56 that it shows the S block, which is the first 2 groups, and this helium should really be over there. And then we have in the middle, this is the D block, the transition metals, and then we have this other section over here, which is the P block. Okay, and so electrons like to exist in these different orbitals. Just so I can show you how it works. If we start off wanting to know, for example, let's say we want to consider sulfur. Now sulfur on the periodic table is in the 3rd row. It's atom number 16. And so I'd look at this and I'd have 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. Then in the 3rd row now, 3s1, 3s2, 3p1, 3p2, 3p3, 3p4. So hopefully you've got your periodic table nearby. So just write out what that would look like. It would be 1s2 for the 2 electrons, then 2s2. Again, these big first numbers indicate the period number. Then we finish off the second row with the 2p block, so it'd be 2p6 because there were 6 of those in there. And then we start on the third row, so we'd have 3s, and we had 2 of those, and then we would go across to this the 3p block, and sulfur was the 4th one along. If we had went all the way to say argon, it would have been 3p6. If we had went to chlorine, it would have been 3p5. Okay, so we know there's 16 electrons in sulfur, and if you added up all these numbers for these electrons, the 2 plus the 2, which is 4, plus the 6 is 10, plus the 2 is 12, plus the 4 is 16. That's all those electrons are accounted for. And so all this is saying is it'd be very messy to draw. But if you started off with a just consider it in 3 dimensions. The 1s orbital would be this sphere in here. So right in the middle here would have the nucleus with all the protons and the neutrons. Your first sphere would be your 1s, and this will get messy soon, but that would be your 1s. And then you go to the next one, which is the 2s's, and so you'd have 2 electrons in this 1s. Then you'd have the 2s. Then we'd start with our 2p's. That would be the 2pz, the 2py, and then you'd have the 2px. So these, I'll just put 2p here. And so then you'd have the next one, which would be the 3s, somewhere like this. And then you'd have, again, you'd have the 3pzs, 3pys, and the 3px's there. And you're not expected to draw this, but this just explains how these orbitals all overlap on top of each other. Okay, so and if we were looking at d orbitals, which would be some other element that we'll cover in a minute, it would get even more complicated again. And so just from what we've got, we know that 2 electrons are in that initial 1s orbital, and then another 2 electrons are in the 2s orbital. I don't know if you can make that out, but it's there. And then you'd have the 2p6s, which were these original p orbitals. That would have 6 electrons in there, 2 in each of those p orbitals. Then we have our 3s2, which is this outer sphere, and then there's 2 electrons in that, and then we'd have 4 electrons in our 3p orbitals. Okay, and that would be that one of those p orbitals has 2 electrons, and the other 2 just have 1 electron each. So if we were to draw this out as a box configuration, it could be drawn like this. We'd have our 1s, our 2s, our 2p, our 3s, and our 3p. And so the 1s has 2 electrons, one will be spin up, one will be spin down. The 2s also has 2 electrons, and then watch how I fill up the 2p orbital. This is the box configuration. You fill up one at a time, because the electrons, out of preference, will want to be on their own if possible. In the same way that when you sit on a bus, you don't normally, unless you really know them, you don't normally sit right next to someone. You'll take a seat that separates you somewhat, just out of comfort and so forth. in the same way, the electrons like to be alone where possible. Now, in the case of the 2p orbital, there's 6 of them, so there really isn't much choice. But the remaining electrons fill up like that. The 3s, we have our 2 electrons. 3p, again, we fill it up like this. So there's 4 of them, so 1, 2, 3, then I go back to the start and put the 4th one in. And so you do this rather than what some students incorrectly do. They would represent that 3p orbital like this and have one vacant orbital, which energetically is really unfavorable. The electrons would rather spread out. So let's have a look at another one. This time we'll look at some d orbitals. Now, if you pick an element, say like cobalt, now cobalt sits on the periodic table right here, and it's in this D block. Okay, so what we have to consider is these d electrons. Now, up until now, we've had the 1s, 2s, 2p, 3s, 3p's. This would be the 4s for these two. So 4s1 would be calcium, 4s1 would be potassium, 4s2 is calcium. Then we're actually into our 3ds. Okay, so even though this block here is in the it's in the 4th row, it's actually at the 3rd energy level. And I'll show you a way to consider that in a minute. So we have our 3D, and there's 10 of them, and then you'd start into your 4Ps. So if we take the example of cobalt, all you have to do is you look at your periodic table, and so we'd have 1s1, 1s2, 2s1, 2s2, 2p6, 3s2, 3p6, 4s2, then 3d, 1, 2, 3, 4, 5, 6, 7. It would be 3d7. So let's write that out. So it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. And so the d orbitals in this case are actually higher in energy than the s orbitals here. Even though this is a 3, it's supposed to be at the 3rd energy level, it's actually higher in energy than the 4 at the 4th energy level. And there's a way that you can remember this, and this is the way that I was shown. Is if you look at the 1s and then 2s, 3s, 4s, 5s, 6s, 7s, and then we go on to the p orbitals. And so each time, in order to have a p orbital, you have to be in the 2nd row. In order to have a d orbital, the d orbital start in the 3rd row. In order to have the f orbital, which your book will mention, you have to start in the 4th row. Okay, so here would be 2p's, 3p, 4p, 5p, 6p, 7p, and then we have our 3d. So this would be the rows with the columns with the s's, columns with the p's. Now we're doing the columns with the d's. 4d, 5d, 6d, and we really don't have 7d's. So then we want to look at our f orbitals. We start off with 4f and 5f. Okay, so on the periodic table, let's have a look at these. So as I've indicated here, we have 3d, 4d, 5d, 6d. That's actually here in this middle block, this D block. So we started scandium. That there would be 3 Ds all the way across in that block. 4D, 5D, 6D. In here, this section where it's got that gap, and it's written out here, these would be your F orbitals. So this would be the 4F orbitals and the 5F orbitals. We won't question you on the F orbitals so much. So one way to look at this is to draw a diagonal arrow across that shows the way that these energies go. And so we go 1s first, then 2s, and then it goes 2p, 3s, and then we go down to the 3p, then 4s, and then the 3d, 4p, 5s, and then the 4ds, the 5p's, and the 6s, and then we go through this way. Okay, so you can see that's why you go through to the 4s, then the 3d, then the 4p, if that makes sense. This sometimes can be more difficult to remember than just remembering that the first transition metals are basically 3Ds. That's how I remember it. If I can remember that, then the rest of it's quite easy. You know, because this is, everything here is like a 1s, then 2s, 2p's, 3s, 3p, and 4s, 4s1, 4s2. Then I know that it's 3Ds through there, and back to the 4p's. And then this row here will be 5s, then it's 4Ds through here, and the 5Ps. Again, if you can remember that this first row of transition metals is the 3Ds, then it naturally follows that must be the 4Ds, this must be the 5Ds, this must be the 6Ds, and the Fs are the 4F and the 5F. For me, that's easier. And then if I want to know the order, I don't have to try and remember something like this. It's easier just to look at them in order and know that the 4s comes first, then the 3Ds. The 5s comes first, then the 4Ds, and so on. So I hope this helps with writing your electron configurations. And then the next section of the book discusses the valence electrons. And so when we look at valence electrons, we just sort of combine all these together. And so as long as they're at the same energy level. But the book does a pretty good job of explaining that. And so as long as it's in the same energy level, then it's considered that all valence electrons are available for bonding. So perhaps we should do a quick example with, say, chlorine. So if we have a look at chlorine, the electronic configuration, it's a 1s2, 2s2, 2p6, 3s2, 3p5. If we look at the periodic table here, we'd have our 1s2 for hydrogen and helium. We have a 2s2, 2p6, 3s2, 3p1, 2, 3, 4, 5, 3p5. And so the valence electrons are considered those in the highest energy level. So in this case we're at the third energy level, and so there would be 7 valence electrons, which would be the 2 from the S's here and the 5 from the P, which gives a total of 7 valence electrons. What happens is that the S orbitals and the P orbitals will go through a process known as hybridization, and so instead of having one sphere and these 3 different P orbitals, they will merge into some other shape, which would be in depending on what's bonding, and you could have all different mergings, but it will always be, in the case of chlorine, such that you'll have 7 valence electrons. It may not be that all p orbitals hybridize with the s orbitals, but you'll always have 7 valence electrons. And just while I remember, this can also be written as neon and then the rest of the structure, which would be 3s2 3p5. This is often known as the noble gas configuration, because we want this way of writing it greatly shortens what you have to do. So for instance, we're going to consider something like, say, bromine. Now bromine's in that 4th period. So that 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, or sorry, 4p5. Instead of going through all that, you could just go to the noble gas that occurs on the row before, and so the noble gas there is argon, and the argon can just be written in brackets, and then you just start with 4s2, 3d10, 4p5, which greatly shortens it. And so in the same way, that's why we have neon 3s2, 3p5 is also acceptable for chlorine. Okay, so I hope those examples help. And if you're going to write it out like this, it always has to be a noble gas. You don't just sort of pick any element at random. Like I can't just, you know, if I was going to do bromine again, I wouldn't just pick selenium and then just add an electron somehow. I always go back to the noble gas, because the noble gas tells us that everything under here, everything below this 4th row, is full. Okay, once I've written that noble gas, and it's not reactive. But in the final row, there could be some reactivity there because the valence electrons merge, as we just discussed. The orbitals can hybridize. And so I'll leave it there. And please just give me an email if you have any other questions about this. I know it's a difficult topic, and if you email me or perhaps call me, I can help you. Thank you.